Good morning. This is the second lecture on similarity analysis. The contents of the lectures are similarity rule, specific speed, specific diameter, the impeller design versus specific speed, impeller efficiency versus specific speed. So here, a lot of importance I have given on specific speed. I'll discuss here about the similarity rule. Let me consider turbo machines of similar design operating at high Reynolds number, thus neglecting the effect of Reynolds number and cavitation. And then we land on the following relations where xi, phi and p tilde are constant, where phi is given by q divided by n dq, xi gh divided by n squared d squared, and p tilde is equal to p divided by rho nq into d to the power 5. Now, from this relation, we can write h proportional to n squared d squared and q proportional to n into dq for dynamically similar machines. And thus combining these two, I can write q also proportional to d squared into root over h. Similarly, p proportional to nq d to the power 5 and replacing n, I can write p proportional to d squared h to the power 3 by 2. So these are the important relations for similar machines or for machines with dynamic similarity that can be remembered. To discuss further, I have considered a model and a prototype which are dynamically similar machines, and the machine of same design. Thus, definitely they will have the similar velocity triangle. So the velocity triangle, exit velocity triangle of the model, and if you see that of the prototype, they are similar triangle. That means the ratio of corresponding velocities would remain invariant. That is, u2 by u2 dash is equal to w2 by w2 dash and c2 divided by c2 dash. Furthermore, the corresponding angles between the two triangles must be same. That means beta 2 must be equal to beta 2 dash and alpha 2 must be equal to alpha 2 dash. So thus they are the similar triangle. Now if we go further, how their characteristics would look like. Here I have shown you the characteristics for the model and the characteristics for the prototype, which are independently tested, and they are represented in HQ scale. Look, star is the data point for the model and the corresponding data point for the prototype is circle. And look, I have marked a point on the prototype by capital M, for which the machine is designed for this combination of H and Q. The machine is designed. That means at this point M, it will give maximum possible efficiency. The corresponding point in the model is represented by small m. And let D1 and N1 be the diameter and speed for the prototype, and D2 and N2 be the diameter and speed for the model. Now, if we represent the characteristics where H and Q are scaled by N square and D square, so H has been scaled by N squared D square, whether Q has been scaled by N D to the power Q. So what I have shown, then the data sets from the model and that from the prototype are exactly superimposed each other, producing a unit characteristics. Thus, I have written here the characteristics curve, that is H by N squared D squared versus Q by N dq, that means xi versus phi characteristics for the model and prototype would perfectly superimpose, representing a unique dimensionless characteristics. What we have learned from here? This is the representation of dynamic similarity. And further, the utility of this non-national curve is, suppose if I develop the model and test the model and produce result in xi phi form, that is non-national form, then that non-national characteristics would also be valid for the prototype. Now, if for the same machine the speed has changed, how the characteristics will change, that I have represented here. Now, you see, this is the characteristics for the speed of the machine at N1 RPM, the next one N2 RPM, and then that is further higher RPM at N3. So N3 is greater than N2. Similarly, N2 is greater than N1. So it will be parallelly received if I consider the local dynamic similarity is maintained. I'll discuss about the specific speed now, which is a very important parameter in turbomachinery applications. The turbomachine designer is often faced the basic problem of deciding what kind of machines will be the best choice for the given duty point. Now, what is the duty point? Duty point is the combination of NHQ for which the machine would be designed. Any vendor to any producers of turbo machines, they specify this duty point. So for a designer, only head developed by the machine, flow rate, and the RPM is known. Now he has to decide first what kind of machine he would design, whether axial, mixed flow, or a radial flow, and what would be the maximum possible efficiency. With respect to this, the two non-dimensional parameter called the specific speed ns and the specific diameter ds are often used to decide the appropriate machines which will provide the maximum possible efficiency for the design condition. Now, the rest of the portion I have discussed with respect to a turbine, considering the flow is incompressible. So I have defined first what is called the specific turbine. With respect to these, the specific turbine is defined as the machine that produces unit power under unit head. And the speed of the specific turbine is called the specific speed. So now you know what is called a specific turbine and what is a specific speed. Now let N, D, H and P be the speed, diameter, head and power of a prototype turbine. So we know P proportional to D squared to the power H to the power 3 by 2 and H proportional to N squared to the power D squared. So thus, from this relation, I can write D squared proportional to H by N squared. Now, in this P relation, that is P proportional to D squared H to the power 3 by 2, I can replace D squared by H over N squared. So I'll get P proportional to H over N squared into H to the power 3 by 2. Thus, we'll get P proportional to H to the power 5 by 2 divided by N squared. Now let us consider Ns, Ds, Hs and Ps be the speed, diameter, head, power of the specific turbine. Therefore, we can write P by Ps is equal to H to the power 5 by 2 by N squared into Ns squared by Hs to the power 5 by 2. And therefore, from here, we can get Ns is equal to root over P by Ps N into H S by H to the power 5 by 4. So I get a relation for Ns. Now here put Ps is equal to 1 and Hs is equal to 1 as per the definition of specific turbine. By putting Ps and Hs as unity, I will get Ns is equal to N root over P H to the power 5 by 4. This is the expression for a specific speed of a turbine. I have expressed here the physical significance of specific speed, such as all similar machines operating at similar condition will have the same specific speed. Hence, the specific speed is a single parameter to characterize the machines. To explain further, I like to say the two machines, if they are designed on same philosophy, the specific speed must be the same. Furthermore, the Ns can be expressed as Ns means specific speed as Ns is equal to N root over Q H to the power 3 by 4. This expression will get by replacing P as P proportional to Q into H. Now this expression of Ns is called volume specific speed and is defined as the turbine that allows unit discharge under unit head. Now another point I like to say here, what is the disadvantage of the expression of specific speed that I have derived right now? The disadvantage is the specific speed of a same machine defined in two systems of unit are different. That means their system of unit dependent. So it is always better to deal with a non-dimensional parameter. With this respect, I have defined the non-dimensional or dimensionless specific speed as, which is expressed denoted by small ns. Small ns is equal to omega into root over q by gh to the power 3 by 4. Now omega is in radian per second. The diameter of a specific turbine is called specific diameter. Let me derive the expression for a specific diameter, which is very easy, that we know Q proportional to d square root over h. Thus I can write Qs by Q is equal to ds by d square into root over hs by h. And from here I can get ds is equal to root over qs by q into d into h by hs to the power 1 by 4. By definition, for specific turbine, qs and hs are unity, and hence put the value of qs and hs in this expression. You will get ds is equal to d into h to the power 1/4 divided by root over q. This is the expression of specific diameter. Now, the non-dimensional or dimensionless value of specific diameter can be expressed as a small ds is equal to d into gh to the power 1/4 divided by root over q. So this is capital DS specific diameter, and this is dimensionless specific diameter small ds. By a schematic, I have shown here how the impeller design changes with specific speed. Look, as specific speed changes, the impeller design changes from radial, mixed flow, and then axial flow impeller. So in this region of specific speed, which is of lower region, you will get radial flow impeller. In the middle region, we land to mixed flow impeller, and when the specific speed is more than 10,000, will land to axial flow machines. Here specific speed has been expressed in terms of Betis unit, not in SI unit. In the next, here I have expressed the efficiency versus non-dimensional specific speed, small ns. in reality, and you can appreciate that the value of Ns lies in between 0 to 5. And I have expressed in terms of turbine. Suppose at less than zero point 0.5 Ns, the region for Pelton turbine, and zero point 0.6 to 2, the value of Ns, the region for Francis turbine, which is the mixed flow machines, and 2.5 and above is the region for axial flow turbine. Thus, with this figure, one can appreciate how the efficiency changes with specific speed, and one can further appreciate that the Francis turbine and axial flow machine maintain high efficiency than the Pelton well. Thank you for listening.